Okay, great. Good morning, folks. My name is Richard Sharpe, and I work for a company called Hammerspace, but I also do Wireshark development work and so forth. So what I want to talk about today is a bunch of topics around generating Wireshark dissectors, and because there are some interesting things that you can do once you have a description of a protocol. And you can't really extract easily, at least, a description of the protocol from a C dissector or a Lua dissector. Although, of course, if you were using WSGD, that is a description that you could form or translate into another one. Then I'll talk briefly about what a dissector is, because during yesterday's dinner, I discovered that there were people who weren't clear on what it is, and so I have a view of what a dissector is that's not related necessarily to the chunk of code that you will write to create a dissector, and then try to motivate why you would want to generate dissectors, and then after that talk about this issue of should you generate C dissectors, should you generate Lua dissectors, and what are the advantages and disadvantages of each of those. And finally, and then look at the language that I've come up with to describe the protocol that you're trying to generate a dissector for, and then along the way have a look at what it does in transforming that. And then I'll go through some examples. And these are all based around Graham's protocol. I found his protocol both had enough interesting things in it that forced the code to deal with some more complex bits and pieces, and that because some people are familiar with it because they've sat through Graham's class and his talk, then it helps because of the familiarity. And then I'll talk about where to next, where the code is and things of that nature. Now, after I've introduced myself a little bit, I'm going to also ask you guys what your interest is in this topic as well. And partially that's because we have a lot of time to burn today as well. So I've contributed to Wireshark, or it was, ethereal back in those days, since about 1999. And as I said this morning, that was because I had a need, and ethereal was close to fitting my need, and I had the source code, so I could go and modify it to do the things that I wanted at that time. And I've kept on being involved with Wireshark, although for a bunch of years I was not very much involved, but I've gotten back to being involved in the last 5 years or so. These days I do a lot of work on 802.11 and things like helping out with the new 802.11 AX standard and the 802.11 AI standard, also known as sub 1 gig. It's the version of 802.11 for 800 and 900 megahertz. Which has the advantage of, whilst it has the disadvantage that you get lower bandwidth at 800 and 900 megahertz, it has the advantage that if you put an amplifier on, you can get distances of as much as a kilometer out of sub 1 gig. And so there's a lot of work going on there. Now, part of the reason I got involved or interested in generating dissectors is that I created a dissector generator that's used in the company I work for, Hammerspace, a few years ago for XDR-based protocols. Who knows what XDR is? Anybody here know XDR? XDR is a protocol description language that was developed by Sun Microsystems and was used to describe NFS, the NFS v3 protocol, and generally is used to describe RPC protocols, remote procedure call, or one flavor of RPC protocols, because there are other RPC protocols out there that have their own description languages. And internally, we use a lot of RPC protocols. We use about 12, I think, RPC protocols between the various parts of our software. And what was happening was sometimes someone would write a dissector in C for one of these protocols, but then they wouldn't keep it up to date because during the software development process, the protocol will change as you discover you need more things in it, or you need additional requests or things of that nature, and people were not keeping the handwritten dissectors up to date. And I realized that by modifying a tool called RPC Gen that is used with XDR to generate the client and server stubs for XDR protocols, where the client stubs you link with your program, and that does an RPC to the server, and the server stubs are responsible for receiving those requests, handing it up to the application, and then taking the responses and putting them on the wire and those sorts of things. Given that there was already that infrastructure there for generating client and server stubs, it seemed like it was going to be relatively easy to do the same thing but generate a Wireshark dissector. Now, it turned out not to be relatively easy. It did take a while, and I actually rewrote my dissector generator as well, because my first attempt was really poor and had lots of problems, so I rewrote it. But we use it internally now in production, in that we generate Wireshark dissectors for all of our XDR-based protocols, and our QA people use those when they use T-Shark for checking things on the wire. Then in 2017, I started working on a more generic dissector generator. It was late in 2017 when I started doing that, so I've been working on it for like a year and a half now, and I'll describe some more of that effort later on. And the problem, of course, is that I can only spend time on it now and then, which typically means that I make a burst of activity or have a burst of activity before a SharkFest conference where I'm trying to get something that I can demonstrate. And so I do have something now. Okay, but before moving on, what I'd like to ask is why are people generally interested in dissector generators? What is your thoughts on that?
I'm using it currently at work. Well, it came up by chance. Like my kind of work involves like connectivity to exchanges, and we have a lot of proprietary like protocols.
Right.
So as usually comes, like I'm a network engineer, they always blame the network when it's the server or the application. Because we couldn't see when it was the actual application talking, because it's proprietary.
Yes.
I started playing with dissectors, and then like we started seeing more data, and we could see actually it's the application or nothing to do with the network. So.
Right. So that's actually a very good reason for using a dissector generator. If you have a lot of proprietary protocols, protocols that nobody else is going to write a dissector for, you can employ somebody to write one, and of course they will likely create bugs in the code as well that you'll be fixing. But if you can write a description and generate something from that, and as long as the generator accurately reflects the description, then you've got something that is essentially bug-free. And even if there are bugs in the translation of the description to the code, you fix it once, and then you can regenerate all of the dissectors, and they all should be correct, etc. Anybody else?
I've got to modify the DMP3 protocol to decode secure authentication.
Right. This is probably not going to help you at that stage. I'll tell you why towards the end. Any other? Yes?
Just looking at various protocols, you have people who are developers and who actually know how to do programming, but then there's the rest of us who maybe had a little bit of experience in college, but it's not something that we commonly do. So
right.
Something that'll actually generate it versus us attempting to make some really poor code.
Right, yes, and that's one of the other big reasons is for, and I'll talk about some of that in a short while when I get into it. Okay, let's get in. Feel free to ask questions at any time as well. So, okay. Now, the question that arose yesterday in a couple of occasions during dinner was, what is a dissector? People wanted to know what this thing is. And for those of you who were in Graham's talk or who have messed with dissectors before, it's obviously a chunk of code, but the function of, and that code can be either Lua code or C code today, and with WSGD it can be a description, but that code, the function of that code is to create this stuff you see here in the middle pane on Wireshark. If you place your if you put the tree output in the middle pane. So the function of the dissector is to figure all these things out, like the header, the data, and the various fields, and to insert them into the tree. And so from that perspective, there are typically many dissectors involved when you are dealing with a capture file. And I say typically because if the protocol you're dealing with is sitting on top of TCP/IP, then you will have, and let's say you captured it via, and it's been carried in wireless, then the radio tap dissector will be involved in dealing with that, because there will be a radio tap header in that PCAP file, and then there will be wireless stuff, so the 802.11 dissector will be involved, and then IP, TCP, and then your protocol, whatever the protocol is. And you can think of this as one for each of the headers. And I'm sorry, I meant to draw a diagram, but the concept here is that these protocols out there, there is a sequence of headers, one for each of these things. The radio tap header it doesn't necessarily appear on the wire, of course. The headers, the 802.11 and down headers do appear on the wire, and the radio tap header is a pseudo header or that is inserted by the capture device, but nonetheless there is a dissector for each of these, and they all put information into the middle pane and organize it for you. Some dissectors are small, as we saw. Graham's C dissector that he wrote was about 270 lines of C. And that's kind of about the smallest C dissector you'll see. Some are very, very large. The 802.11 dissector I looked at earlier today, I think, was around 36,000 lines of code. And partially that's because the way that the 802.11 folks do not, they whack everything together into this one standards document, and the standards document now is like 3,600 pages of stuff as well, that includes both the wireless level stuff, as in the radio transmitter stuff, that sort of stuff, as well as the packet formats and the procedures for how you deal with all of that. But still, because they didn't break it up in a neat way, the dissector itself hasn't been broken up too well. And some of them do quite complex things where they keep track of state information. And I'm telling you all of this so that you understand some of the deficiencies of what I currently have. But when I say they keep track of state information, the sort of thing that they do is they track, if it's a TCP/IP connection, then there is tracking kept of the source and destination information, and say the SMB protocol or the NFS protocol will record for that, what's called a conversation, will record information about various things. They will record things like the file IDs of open files so that you can match it so that when you display this information in the middle pane, instead of, or rather, as well as putting a file ID in there, you can also put the file name that that file ID is related to, so that people can make better sense of what's going on. It also does things like record information for each packet about what's been seen in that packet that might be useful later on while it's dissecting, and it keeps track of for every response, it will keep track of which frame the request appeared in if they know that information, so that it can print out things like the round trip time for requests and responses, i.e. when the request was sent, and so that you can do those sorts of things. So dissectors can be actually quite complex. What I've got, the code that I generate at the moment, is nowhere near as complex, but you'll see what I've got, and you'll get some sort of an idea, hopefully at the end, of where I would like to take this as well. And so, yeah, let's see. So now, the question was, why generate dissectors? And we heard a couple of answers there already from people. And the hope here is that it's easier than writing them, and it certainly is easier than writing them. And my next point, but I'll come back to this one, is that dissectors are quite boring to write as well, because you're typically writing the same sort of stuff over and over and over again. Because to give you an example, when I was working on the multi-AP protocol, they had a whole series of TLVs, type length value objects, that appear in the multi-AP protocol, and many of them had very, very similar fields in, and so you're writing some code to dissect that same field for every one of the requests, and you're generating those header fields that Graham talked about during his talk for every one of those as well. And typically you want to generate separate header fields because people want to be able to search on those based on the actual, say, the TLV, and be able to differentiate between those various things. So it can be fairly boring, but if it is easier than writing them, especially if the language is simple enough that you don't have to deal with C, and you don't have to deal with making decisions about how the stuff is going to be displayed. If we can absorb all of that in the language, and if the language is expressive enough, then we can do quite a bit around generating dissectors. And as I mentioned before, when you find bugs, it's easy to regenerate the dissector. The bugs may be either in the description, your description may not be quite right, or the bugs may be in the dissector generator. But once you have a description, you can run it through. You can either modify the description and then run it through the dissector generator and generate a new dissector. So it can give you quite quick turnaround time as well. If you have a lot of proprietary or obscure protocols that you're dealing with, there can be a lot of man-hours invested in writing those. And if the protocols are changing, then someone has to also be around. You have to employ someone or what have you to modify the dissectors as well. And so the other thing that you might want to use generation for is that there is the potential to generate other things once you have a description of the language. And one of those things, and I'll mention it again later on, I believe as well, is you could generate a PCAP file full of randomish packets that have data in them based on the protocol description. Now, why do you think you might want to generate a PCAP file of data for this particular protocol? What would you use such a thing for?
figure out function code?
Well, to figure out the function codes, yes, but there are some other reasons.
You can just make sure that you're.
Yes, precisely. You can test lots of things. There are tools, and especially when you're developing protocols, often what happens is you write the protocol client and server code, and hopefully that's working correctly. But in order to verify that it's working correctly, what you really want is a Wireshark dissector before the code even is started, so that you can capture these packets and then verify that you've done it correctly. But then you need to ensure that the dissector is doing the right things as well. And so you could generate a PCAP file, run it through the dissector, the generated dissector, and verify that it's doing the right things, find out if there are any crashes or anything like that. You could generate invalid data as well and verify that your generated dissector is doing the right things with invalid data. And there are other tools out there that will take a PCAP file, modify some parts of it, like the IP addresses, and then shoot it at an implementation. So you can even use it, because typically you have, say, a different team doing the client than the server, or at least different people doing the client implementation than the server implementation. And so the server guys can test their code before the client guys have their implementation ready by shooting these generated packets at the server. So there are a bunch of advantages or other things that hopefully at some stage I'll be able to manage, and a lot of these ideas that I'm talking about are because I happen to work on protocols like SMB, NFS, and other protocols at work where I work. And as somebody else already mentioned, more people now can generate or produce dissectors, especially for their own environments where they don't necessarily want to release the code. And also, of course, writing dissectors is hard. There's a steep learning curve. You have to create a build environment if you're going to write them in C. Even if you're going to write them in Lua, you have to understand the Lua functions in Wireshark, and you have to understand how these things map on to the things that Wireshark, the functions, the features, and the provisions that Wireshark has. And the other thing is that Lua is quite a different language. It's a scripting language, but it's quite different from C in terms of its capabilities. So sometimes it can be hard to move backwards and forwards between Lua and C. And that some of the features in Lua are similar to what's available in Python, for example. And we'll probably have a look at some of the Lua generated code during the rest of the talk, and you'll see that there are things like functions can return multiple values. They can return a list of values in Lua, which turns out to make life in generating the dissector a little bit easier, although the way you deal with that in C is you pass those fields as extra parameters, as pointer parameters in C. But yeah, so... and here is this discussion. I've preempted some of it already around, the C versus Lua, but let's just go through it. So the obvious choices, of course, are C and Lua, because both of those are available in Wireshark. And C, because a lot of dissectors are written in C, and so you can there's a lot of code there. You can go and look at existing dissectors and see what they do, and use that then to as a guide for your own dissector. However, of course, you have to get over the learning curve and figure out what all of those functions are all about. Lua is useful because you don't need a development environment. If you are developing in C, then you need to put together a development environment. You need to pull down the source code from review.wireshark.org or wherever, You need to make sure you have all of the requirements like the C compiler and building tools and Git and all of those sorts of things. All the right libraries need to be in your development environment, or you can't do anything, you won't be able to build. And also, it takes a while to build. Although I notice these days, once you've built the first time, it takes maybe 10 or 15 minutes to build Wireshark completely on my laptop the first time. And I typically run in a VM, running some Linux distro on a VM, and it's taking 10 to 15 minutes to build the first time. But then after that, because we're now using dissector, Ccache, because we're now using Ccache, subsequent builds can be very, very fast and maybe a minute, because generally you're not changing all that much, and it keeps all of the old compilation artifacts around, so if a file hasn't changed, it doesn't have to recompile it. Now, and as Graham mentioned, if you write in C, the dissectors are going to be really, really fast, compared at least for Lua. The dissector will be slower, but you will get a faster turnaround time. However, because the dissector generator that I've been working on can generate both C and Lua code, as long as both of those generate the same results, and I need some sort of infrastructure for verifying that they do generate the same results as well, then once you've got the Lua dissector working and to your satisfaction, you could then turn it into a C dissector and employ someone or go through the effort of getting a build environment for yourself and just plunk the C dissector in there and then build. And now you've, in some sense, you've got the best of both worlds. You've had the convenience of quick turnaround with Lua, and then you can convert it into something that's going to be quite a bit faster. And Graham was mentioning, I think, that it was something of the order of 2.5 times or more faster between the C and the Lua dissectors. What is Lua? Then, well, there's a description out on the web that you can find. It's an embedded scripting language, and various folks use Lua. The Wikipedia folks use Lua in MediaWiki. A bunch of other people use Lua as a scripting language that you can use inside whatever software you're developing. And quite a few years ago now, the Wireshark team decided to add Lua support to Wireshark, and it's quite mature. However, Graham alluded to the fact that not all of the features are available. Certainly, about a year ago now, I think, I found that that Wireshark range strings, in Graham's talk he showed you value strings where you set up a list of values and the strings that those values translate to. Wireshark also has the concept of range strings, because a value string can be a pain if you have, even if you've got some field that is a uint 8 bits long, but you're only using a few of those values, and similar to what Graham was using, you're only using a few of them, but you want to be able to have your own error message for the undefined values, because the default Wireshark behavior will say unknown in there if you trying to translate a number into one of these strings using a value string. There is an alternative called range strings where you can say from this number to this number, the value associated with it is XYZ. And with his example, there are in fact several ranges that are undefined, and you can use range strings now in Lua to handle that. But Wireshark also defines range strings and value strings, and 64-bit versions of those as well, because of course it started out on 32-bit environments, but now there are 64-bit environments. And the 64-bit range strings are not implemented in Lua, and there are a few other things that are not implemented in Lua. However, that shouldn't be a problem for the code, my code at the moment at least. It allows you to write dissectors in Lua, and you can do other things with Lua. You can modify the UI with Lua as well, but I'm not interested in talking about that here. Now, so my getting on to the generator, and we won't look at the code, and you'll see why. The code, it's the generator code. We will look at the protocol description language, and we will probably look at the Lua code that it generates. And I probably won't bother. I may show you some of the C code that it generates for the same protocol as well. But, I had fairly modest requirements. Should be a relatively simple language to describe a protocol, so that, and it should be kind of familiar to many people who maybe had a smattering of programming before, or who have a knowledge of protocols, and understand that these things have like 8-bit fields in them. They have bit fields. There are some of these fields that need to be split up into bit fields, those sorts of things. And it should handle pretty much all of the sorts of data types that you would see. It should handle little endian and big endian versions, and you should be able to mix and match them, because there are some protocols that do mix and match little endian and big endian. And 802.11 has a tiny amount of mix and match in that sense. It should support bit fields, as I mentioned. It should support exceptions, and we'll see that in a short while. None of Graham's code showed how to handle exceptions, how to tell the user that there's something wrong with the data, Wireshark will, of course, normally, if the packet is too short, you will see one of these malformed packet exceptions thrown, but you might want to do other exceptions. You might want to alert the user that some of the values in there are incorrect for the protocol, and it would be nice to have an easy, simple way to indicate that in the protocol description language. And it should support some extra annotations, and I'll tell you what I mean by that in a short while, but it relates to some of the things that Graham showed. So going further on the language, it's basically what you describe is a bunch of data structures, and those data structures contain bit fields. They might contain some of these basic types like uint8, uint16, uint16 under little endian. And so I went with this approach, where you simply append under little endian or under big endian on the data type where that matters. So things like uint8, it doesn't matter at all, of course. And there are some others the language also actually allows you to declare at the beginning of a file what the default data type is. So then you don't even have to bother. You can just say uint32. But there are things like byte strings, etc., for which you don't need to care about whether it's little endian or big endian. And I provide a switch statement in there. And this is something that I kind of got from XDR, where they do the same. And a switch statement allows you to fairly compactly represent protocols where they have a command field at the beginning, and then the rest of the structure depends and differs depending upon the command field. But it can also be used for if-like statements, and I'll show you some of that in as well. I have arrays, because arrays turn up very frequently in protocols, and the controlling length can be either a literal string, like the number 6, or it can be a field that has occurred earlier in the dissection. And there's a couple of other kind of tricks that are there as well for allowing you to manage these arrays. And there's a bunch of extra glue in there So let's see, the example is Graham's protocol. So let's now briefly go, and so here I'll switch to a terminal and show you what the protocol description language shows. Now, is that readable at the back there? Hopefully it is. So, and some of this will be familiar when you saw Graham's example. Let's see, is it readable back here? Yep. Okay, so basically the language allows comments with a pound character. So anything after the pound is a comment. And then there is a statement that allows you to specify what the endianness is, what the default endianness is. And so in this case, it's big endian because Graham's protocol is mostly big endian. And then there's this enum thing, which declares these values that he used in his protocol. So the connect function had a value 20. And there's a string associated with it. In this case, I've chosen to associate the strings with these enums, and I'm specifying the size of this field here in the definition of the enum as well. And there is a default value. I've added a default value to this thing so that you can specify what should happen if it's handed a value that is none of the above. And so you get a default translation. And so there's a couple of these enum-like things in there. Then you just declare a bunch of structures. So there's a request-reply data structure in there that is handling one part of it. And the way I have written this, however, is the main part, and this is Graham's proto. It's possibly better if we go down to the bottom here. What it says down here is this is some of the boilerplate information that Wireshark needs. It's giving these details, like this is the name of Graham's protocol, and there's currently a bug in my generation code because we should be labeling things as this rather than that, which I'm putting on the wire, but these are things that Wireshark needs. And then this is the dissector entry point saying that Graham's proto is, the dissector entry point is Graham's proto PDU, which is this structure up here. And then this last thing is telling Wireshark which table this dissector hangs off. So it hangs off the ether type table at 89.3c. And the reason I did this was I wrote some code to generate a packet capture for Graham's protocol that, but I didn't want to write code to generate the IP header and the TCP header and stuff like that. So I just said, hey, let's just make this an Ethernet type of protocol. But you could simply change this and put it in the TCP dissector table and specify the port number as whatever port you want, and then regenerate the dissector, and it should still work with Graham's packet captures. And I've done that in the past, and so it seems to work okay. Now, so this is the main structure in this protocol here, and there is a header at the beginning. So, and that header is defined up here. Here is the structure name. So this header has a name called header, and I've just put a uppercase H in there for the name. And you'll see there are a number of places where you can either put in a quoted string. If the string that you want to use has spaces in it, then you need to put it in as a quoted string. Or otherwise you can leave it as a bare string like this, and it will insert that at the appropriate place, and we'll see that in a second. It'll insert that in the code. And then I use this switch statement here to determine what the rest of this packet contains. And this switch statement says, hey, go to the field called header, which is immediately above it, look inside that field for a field called function, and use that value to determine what we're going to do here. So you can reach into other structures, and you can reach up from structures down below if you need to, back to structures above you to find the fields that you need. And when I wrote this, I thought about using a dot notation for these things, but then I thought, hey, wait a minute. Most people are familiar with file or path names in Unix and Windows, although Windows uses the backslash. So I decided to use slash in here, and there are some, maybe not in this protocol, but in other protocols that I've worked on while I'm been testing this. There are some cases where you can say things like ... slash, and so it's saying go up one level from where we currently are and then go down from there. So I've tried to build in a bunch of flexibility there. And then in this case statement, in here, or rather the switch statement, in each of these, you can have either just basic data types in here with names associated with them, or you can specify some other value that you've defined. That one is an enum, and or you can specify a structure which is defined up above, and we can go up further up. Oh, and then lastly, there is this little thing here, and I'll talk about this some more, but there's a couple of special variables that are associated with this, and this is a kind of an if statement. What it is saying is, look at the remaining bytes in the TVB. Now, Graham mentioned this thing called a TVB, the testy or testable virtualized buffer, virtual buffer. These are the objects that are given to each dissector, and it's designed to prevent dissectors from running off the end of a buffer. And so this switching, this remaining in particular, extracts the value of the remaining bytes in the buffer, and you can use it for doing error checking here. And, in case that there are no bytes left, this is the sort of thing you would do. I've seen a number of packet captures where the protocol, the developers have screwed up and they've sent more data than they should have, and it's sitting there off the end of the last part of the packet. And so you might want to, rather, if the value of remaining is 0, then you can use this field called void. And what void does is it says, don't do anything. There's nothing for you to do here. So this is really an if statement, which is saying, if remaining is not 0, then insert this element into the what Wireshark is going to show, and this element will have a length. This is an array with a length of remaining, so that you can actually handle every single byte that's in the buffer there. And if we go up and right, and here is an example of this exception case. And you can insert switch statements inside of other switch statements. And so what I've got here is, if this request was a read short, then there is the read short data type there that's going to be dissected. But then we're going to, and here's an example of using this ... notation. We're going to go up one level and look at header, and inside header look at length. And if the length is 6, then we're not going to do anything, because that's the correct length for this type of request. But if the length was any value other than 6, then we would insert an exception into the Wireshark display, and I'll show you what that looks like in a while when we get to that particular case. That exception has a few values, one called incorrect length, which is just kind of a placeholder in there. And then you can specify what type of problem it is, and you can specify a message associated with that particular exception as well. So this gives you a very brief rundown of the language. So let's go back now and continue on from where we left off, and I may come back to it. So what I've done there is I've described Graham's protocol with a description language, and then, oh, no, wrong way, I went wrong way. Okay, so now what I wanted to point out is that when you define a field here, the name here is derived, actually that's the wrong thing. I've shown the wrong stuff there. Let's go back, but before we go, keep an eye on this field. So this is a screen cap of what a particular packet looks like. This field here called header in uppercase H, that is derived from the protocol description, and I probably should use Control Alt or what have you, but here, this field header here is what gets plugged into there. So the names that you use are plugged in various places in the generated code. So you don't have to worry about how am I going to get these things into those various fields in Wireshark. The generated code will handle that for you. And there are a couple of other cases where this sort of thing happens. And so it's designed to happen pretty much all over the place. And things like these enum strings, you saw earlier there was this big funcs enum that was a uint 8, and it had a whole bunch of values in there, and one of them was request reply, etc. And the generated code is written such that it will insert this label here into this part of the Wireshark subtree, so that all of that sort of thing happens for you automatically. And again, there is this function field, it gets inserted there. Now, there are some deficiencies in what the code does at the moment that I hope to resolve over time, but today, those are the sorts of things that it does. And, okay. So, you know, the sort of thing that would happen is, let's say you have a protocol or you've got a capture of Graham's data, and it doesn't know, Wireshark doesn't know anything about the protocol. And so what you would see is stuff like this. In the protocol field would be the ether type, and it says Ethernet 2, and it'll show you a series of bytes in here for the data. But if you then go and generate the dissector for Graham's protocol, stick it in the appropriate directory, and we'll show you where it goes in a second. You can get that info from Wireshark. One of the other things that happens, I'm going too fast, one of the other things that happens is that now this protocol field has been converted to Graham's protocol. Unfortunately, my generator is not yet good enough to allow you to insert reasonable values in here. And for those of you who were in Graham's presentation, you would have seen that he was the various dissectors he was dealing with all put information in that field. So that's something that I have to work on at some stage. And it may be appropriate. Okay, yes. And I talked briefly about remaining. There is some, there are several special variables that are available, or there will be several special variables. One of them is this remaining variable, and yeah, no, that's fine. This remaining variable, and when you, okay, this is, there's a disconnect here. This is from a different part of, or a different capture, or a different description, but the concept is the same. I'm saying, okay, there's a byte field here, and its label is unknown request data, or unknown data at end in this case, and it goes all the way to the end of the buffer. And so this ensures that you deal with every byte that's in the packet. And this is what happens when you use that exception data structure. So I've copied the exception thing here from that example there where, okay, at some point we've said, hey, there's an exception and I want you to associate the exception with this thing here, ... /header /length. And this is just a convenient label. You need that. The code could have automatically generated it, I guess, but I chose to put it in there. But it's not actually part of the grammar, so we could remove it and improve things. And I'll talk about the grammar and such like in a little while. And then these other values, and then the actual string. And so when you hit that case statement, and I'll go back to it in a second, what happens is this exception is executed and it inserts an exception into the tree, and that ripples all the way up to the beginning. But in particular, it is applied here at this field, header length. See header length in here, header length. This exception field applies there. And all of that information that you've added, like protocol error, incorrect length for read short reply, should be 6. All of that is inserted there. So you get a very easy way to insert exceptions into the dissection so that people can deal with those. And as the other thing that I've made sure is that you can deal with every byte in the packet by using this sort of thing, and there are potentially other uses for that. Right. So what we want to do, so yeah, I'll skip that other one. So I generated a capture file for Graham's protocol. Now the capture file, when I generated it, has some errors in it. And we've seen the dissector, the description of the dissector already, but I'll just go back and refresh that. Oh, I didn't want to do that. Yeah, right. So, for example, here is that exception field that's in there, and here is that unknown request data remaining at the end. And there's a couple of places where this protocol defines unknown function data. This is this particular case is where you failed to handle all of the function types, so there was some inaccurate function type in here. Then you can insert this string unknown function data, and there it is, the remaining data is in there so that people can see exactly what's there. Now this is Wireshark. So here is Wireshark, and firstly the thing to find out is where do you put these, and you find that from About Wireshark. When you want to put Lua dissectors in there, you look in About Wireshark and you go down to folders, sorry, not plugins, folders. You go to folders and there is this field, personal Lua plugins up there. That's where you put your Lua code, and when you place the code there, I've already done that in this case, but the next thing you want to do is you want to go to Analyze and reload Lua plugins, and it will reload the plugin. And in testing the dissector generator, I use this quite a bit. I generate a new dissector, stick the Lua dissector there, and then reload it. And you can see, so it's doing, as I mentioned before, it's not doing anything useful with this field. It's doing something useful with that field, but there's a bug in that it probably shouldn't use that value. It should use the longer string form. And we get much the same sort of information that we had for Graham. with his dissector generators. We've got the thing labeled as Graham's protocol. We've got the header field there, the function, the length, the ID. And in this particular case, there's some unknown data at the end of this dissection. This data was unexpected there. And in fact, the description should probably also be checking this value here and saying, is the length of this packet what I expect? And if it's not, I should also throw an exception or generate an exception of some sort. But you can see some of these exceptions. I'll have to hunt through because they're in various places in here. There's an exception. And in this case, the exception is that the length of this frame is incorrect. It should have been 6. And this is what was causing the length to be apart from the length being incorrect, there was all of this extraneous data at the end, and I'm not sure whether or not the length, in fact, I think that length is also incorrect in that 67 is far too long. The actual length there is more like 25 or 30 or something of that nature. So there are further checks that we could have done using these exceptions. Let me see. So now, and there are several of these in here, not all of them, and not all of those have been implemented, but you can see that it illustrates at least some of the concepts here. Now, another thing to look at is what does the generated Lua code look like? And it looks similar to what Graham showed, and I'm going to have to go to a different directory. Right, and there it is. So this looks very much like, if you remember Graham's protocol, it looks very much like what he had. There is these names, of course, are made up names, and so I didn't put any effort into trying to minimize these names, and it doesn't matter if there's some extraneous or extra things in there. There is one of these function enums in there for each of the various values. I also set up some local values so that we can do if tests with names rather than values. And then I define all of the fields that are defined here. Some of these have weird looking names, but that allows me to have separate fields. If the actual field that it's working with has the same name in different parts of a switch statement, then I can disambiguate these things. But it looks pretty much the same. And then we define all of the fields. The only extra thing that Graham didn't touch was this expert info. This is one of those expert info fields that I'm adding, and it turned out to be relatively simple to add support for expert infos. I'm hoping that some of the other stuff will be relatively simple as well, and we have to define these. And then basically we define a set of functions, and I'll come back to these functions just as Graham mentioned, but all of this code is generated, and then at the very end, we do the last couple of things that are required to hook this Lua into Wireshark's dissector tables, etc. We retrieve the dissector table for Ethernet, and we insert ourselves into the dissector table. And then some of the interesting things here, however, are here is where the header is dissected. And we create a few local variables, one for offset, Offset may not have been, saved offset was needed because we want to set the length of that field. And a few other local variables. There is a tree field as well. And this thing here is the variable that holds the item that an exception will be applied to. And then we just return all of these things as separate values because Lua allows a function to return multiple values. And you can handle that at the call, the point where it's called. And there is, the example is up here. The code doesn't look very pretty. For example, there's this issue here. It's not properly indented because I haven't added support for that. But here is where the dissect header was called. It's wrapping here. And we pass in the buffer, the p-info. We pass in this little t-grams proto, the tree that we constructed here. And we pass in offset, and we pass in the label that will be applied, and we get back these things. We get back this item, we get back the local value that we're going to need later on, and another local value that we're going to need later on, and we get back the offset that tells us how far into the packet this thing has gone. And then we just go along and do a bunch of other actions in here and increment the offset and so forth. And that case statement then, that switch statement, got converted into an if because Lua doesn't have switch statements. So it was converted into a series of if statements here. If the header was connect, or it was connect ACK, or disconnect ACK, etc. And we're inserting the correct things. So that's what this looks like, the code, but it's not very interesting. The code, it doesn't really matter that the code is perhaps not as pretty as it could be because the intent is that this is going to be generated and people will generally not look at this generated code unless there's a bug that they want fixed. Okay, I think there's probably not much more that can be seen there, so I'm going to switch back to the presentation. Yes, okay. So as I say, I generated that capture with those 20-odd packets in it, with those examples. And there's more that could be done in terms of describing the protocol to handle all the errors. And so this can also be used to handle a protocol that you've got a packet capture for and you don't know what the protocol is. You don't have a description of the protocol, but you could actually generate a dissector for it by going step by step, because you can look at this data in here, and actually I will go back to the Wireshark display in a second. But when you look at subsequent packets, you could find that this first number varies in a fairly rational sort of way. And you might surmise that that's a command of some sort. So you could write a short description that says, hey, this is the command, and all the rest of this is unknown data. And so now when you generate the Lua dissector from that, stick it into that directory that I saw before and reload the Lua dissector, all of a sudden you will now get a dissection that doesn't show data. It will show you, hey, there's a command field here by the looks of it, and its value is 14. We don't know what that means at this stage, but the value is 14. And then when you go along a bit further and you look at the next few bytes, you'll figure out after a while that those next few bytes look like 7, looks like a length. Now, in the case of the data that I have, it's actually wrong because I've inserted extraneous data in there. But if you had one of Graham's captures and the capture was correct, the protocol was correct, you would see that length field in there and you might surmise that it is a length. And you would then add that to your description, run it through the generator again, place the Lua file in the correct location, reload everything, and all of a sudden now you've got one more field described. And you can go through the whole protocol that way to get some idea of what it looks like, even though you don't know the actual fields in there. So that it can be used for exploring protocols that you don't understand or you don't have a specification for, that may help you find the specification. Here I was just, I guess, indicating that some portion of this data is extraneous in this thing. This early portion is the function and the length. Okay, now, so what about generated code sizes? The description that I showed you was 73 lines of description there for Graham's protocol. That would increase if I went through and added more error checking. So it would probably grow by another 30 lines or something like that. So it would grow to about maybe 100 lines with all the additional error checking in there. The Lua dissector was 151 lines or thereabouts, and the C dissector that was generated was 291 lines. And the generated code has some bugs. The generating code has some bugs in it with respect to blank lines. So there is actually a bunch of extraneous blank lines in that 291 count, but it doesn't matter. 291 is a reasonable number for, you know, for that protocol, and it's actually close to Graham's, but he's doing more than I'm doing at this stage. So, you know, it would probably grow a little bit further as well. The code, the generator now, the code generator, the code that is generating all of this stuff is written in Java. I'm not a Java programmer, but it's written in Java. And the reason it's written in Java is that I didn't want to have to write my own parser for this. And so I used Antler 4. There is this neat parser generator out there called Antler, and it's at version 4, and it generates Java code for the parser. And it's really actually very, very good, because now we're getting to the turnaround time now and the flow for writing the dissector generator. If I find that I need to change the grammar and add more things, I just change. There's a grammar description file that is BNF, extended BNF, Bacchus Naur format, and the extended BNF, I just change that description, run it through Antler 4, it generates a bunch of Java that will parse those files, and then all I have to do is change my generator code a little bit to take into account the way the parser, the way the language description, my language description has changed. So we have to distinguish between the language description I have for the protocol description language versus the protocol description that you might generate to generate a dissector, and run it through there, make a few fixes, etc. And at the moment, there's about 5,500 lines of non-generated Java code, and there's probably another 4,000 lines of generated Java code, but I don't count that. The 5,500 lines is what I've had to write. It needs a cleanup because I'm not the world's best Java programmer, and so I need to go through and fix it in a bunch of areas. And what I need to do in the longer term is to figure out how to generate a jar file so that people don't have to build the dissector generator for themselves, because at the moment you would have to build it using the Java C compiler, the Java compiler. But it would be much better if I could just ship a jar file for Windows and for Linux, sorry. So yeah, but once you have that then, and I've kind of talked a little bit about the workflow already, the workflow is you write your protocol description, you run the generator, and there's a spelling mistake there, but it's gen dissector, -L for Lua. If you don't specify -L, it defaults to C, and then you give it your proto file, and it spits out on standard out the generated code. So you want to redirect it to some file called packet dash. It really doesn't matter what that file is called as long as it's got a Lua extension. place the Lua file in that place that I mentioned before, that you can find out from Wireshark, then run analyze reload Lua plugins, and now that Lua code is being used. And if anything breaks, then your protocol description is wrong. Then you get to fix it and regenerate and go back to this step here. And once you've got it all correct, then of course you could convert it to C as well, because you can generate C from this thing just as well as you can generate Lua. And the theory is that they give equivalent results. And there is an easy way to check that they give equivalent results as well, because you can use a Lua dissector with T-Shark as well. And so you could run through all of the frames looking at what their output is with a C version and the Lua version, and make sure that they produce exactly the same output in both versions. So, some issues with what I've got. The code is incomplete. In particular, notice this field in the info field. I'm not adding any info there like Graham was in his the handwritten dissectors. So it would be nice if I could add some way to fix that and allow you to easily specify, hey, I want some strings associated with these values to appear in the info field, and I want to append stuff in the info field. And that's next on my list, I guess, to implement. And the other thing is, it would be nice, see here, it just says data. And if you, for those of you who are here for Graham's presentation, if you remember, he actually put this label in there against data as well. And that would be another useful thing that I could add to the description, the protocol description language, to allow you to append strings to these trees here, so that you don't have to open this thing up to know what's inside there. You can see at a glance what type of data it is, and if you're interested, you can open it up and go and look at it. But so there's certainly that I could improve. Other issues, it really is only usable today for complete protocols. So if you've got a protocol, a proprietary protocol, or a little-known protocol that nobody has written a dissector for, then you could use this to generate a dissector for that complete protocol. What it cannot be used for so there's no current way that I've thought of so far to allow you to add to generate code for an existing dissector that is not complete. So, for example, if you wanted to add stuff to 802.11 because the Wi-Fi Alliance and the 802.11 people have added another 1,000 pages to the spec, and you want to go and add it, you can't use this approach because I haven't got any features in there for doing that sort of thing. There's no way at the moment to save info across packets and frames. I've got no infrastructure in there, and so I'd have to add infrastructure to the language to allow you to do things like set up a hash function or set up associations, these associations that Wireshark knows about, so that you can record information that might be useful in later packets from earlier packets and vice versa. So there's none of that available. There's no way at the moment to hand off to other dissectors as well. If you're manually writing a dissector, you can hand off to another one if you know that the payload inside your packet is a known protocol that there is already a dissector for, but you can't do it with what I've got. There's still at least one bug in the generator that required me to hand modify the examples in one place only at the moment, so I need to fix that. And there's only one developer working on it at the moment, and that's me. So there you go. The future, what I want to do in the future with this thing, I want to, I want to add some of the things that I mentioned already, add support for adding text to columns, like the info column, add support for appending text to fields, add support for relating requests with responses. That's an important one, so that you can do response time measurements and those sorts of things. And I want to also create, add support for creating packet generating code. so that you can, so that from this one language description you can spit out a packet generator as well that will generate a PCAP file at a minimum that has valid data and invalid data and those sorts of things. So now, our last question is, I guess, why bother doing all of these things? And some of it we motivated before, but one of the things that I see that's useful here is that you can actually, once you have a protocol description and a language that will parse and process that protocol description, and from that perspective, Java was a useful choice given, I was kind of driven to Java because that was the natural code that Antler generates. But Java gives me the ability with subclassing to actually keep the code reasonably clean and generate different types of things. And so we can generate dissectors. I could generate PCAP files from this stuff. I could generate programs to generate data and send it on the wire, and potentially even generate libraries to parse and produce wire structures to and from data structures, because that's, after all, what XDR Gen, or rather RPC Gen, what the original RPC Gen did with XDR. It generated code to serialize and deserialize these data structures onto the wire. And the other reason is that it's actually quite hard to extract a protocol description from a Wireshark dissector. Whether it's a C dissector or Lua dissector, it's pretty hard because you have to go through and interpret that code. You can extract like XML or things of that nature, but even then it's not giving you a high-level look. What it's telling you is that for this packet, these are the fields and the values that are in there, but it's not telling you, in many cases, what you would want. Anyway, I'm seeking feedback. If you've got any ideas on what you think might be needed, I'd be interested in hearing them. And you can send email, although I didn't put my email address in there, but you can send it through the, and I can tell you my email address if you need to. And the code, when I clean up that last bug that I need to clean up, will be up. Why is it going that way? The code will be up here. There is some code already up in GitLab, but it's a previous generation and it doesn't have all of the current changes that I've got in there. And I will tend to keep it up in GitLab for people who might be interested. Okay, so that's all that I've got to present. Are there any questions about that, or was it too overwhelming or too boring, or? Yes.
So just to make sure I understand what's going on, so you're taking a description.
Yes.
And it was the kind of like, it reminded me of the generic description language that.
Yes.
So it's kind of got that similar.
It's got a similar flavor. I developed it independently, but mostly I copied these ideas from XDR, from the RPC language that Sun came up with. And so, but it's WXGD, I think it is. It's similar in concept to WXGD. But what WXGD does is interprets that on the fly, which explains why it's about 7 times slower than C is, for example. Here, I take that description language and generate C code or Lua code to implement a dissector or whatever you want that handles that description, that conforms to that, or hopefully conforms to that protocol description language.
Do you see yourself trying to integrate it into, like, going into that more, the GD language to be able to maybe parse both of them and be able to take any dissectors to?
I probably wouldn't try to parse both, because I think what can be done is you can transform the WXGD into my format, and then so I wouldn't bother burdening the parser with that, it would probably be easier to write a separate Perl script probably to transform one to the other. And but one of the thoughts that I did have is that you could, in terms of dealing with unknown protocols, I talked a little bit about unknown protocols. You could imagine a facility inside Wireshark where you could go along and highlight a field and say, hey, this looks to me like it's a function field, and you can highlight another field and say, hey, this looks to me like it's a length field, and then have that generate a protocol description, or you might enter a protocol description for that, and have Wireshark then run the Java generator and deposit the Lua code in the correct place, and then you could get almost instant feedback on what you're seeing. Or, there are other things potentially that you could do as well. But so that's at least one thought that I have entertained, but that's a lot of code to write, and I need to get this thing working better first. Okay, but if there's no other questions, then thank you. We'll wrap up, and I'll be around here so you can ask.